million.
For that baseball, you said?
Yeah.
Padres?
Well, Patrick Mahomes is a 10-year, $506 million contract.
Whoa, that's cool.
Yeah.
Okay, so torque. You guys have all heard the word before, right?
Yes.
Lindsay, could you put your computer away, please? Thank you. What is torque? Anyone know?
What was a dog my mom had?
Yep, the unit's over. Torque was the name of a dog. That's it, there's nothing more to it. Class dismissed.
This would be a really bad description, but it's kind of like a byproduct of, not necessarily power, but like just force.
It's related to force, yeah.
Mhm.
Yes.
Is it like tension but for rotation?
Yeah, basically. It's the rotational analog of force. So you're like, well, what's a force? A force is when you, which is actually a kind of interesting question to begin with. What is a force? A force is a thing that causes a mass to accelerate. If you really think about it, right? Like F equals ma. That gives you actually the definition of what does it mean to say the word force? Well, a force is a thing that causes a mass to have an acceleration. So that force could be an electromagnetic force, it could be a push, it could be a fan blowing on something, it could be a lot of things. It could be tension. So with torque, it's the rotational version of that. And so if any of you guys have used a wrench, you know. Here, I'll give you a quick little, there was actually a device that I saw on TV a long time ago that I kind of wish I had sometimes. Although no, because then if I had it, then my wife would be able to open the jars and then I wouldn't have no value.
Oh.
So if you have a jar, oh my God, it's not- if you have a jar, right? You try to open the jar and it's not opening, right? What's the
Break it.
Yeah, break it. There you go. No, there's a device they sold that. Oh, yeah, I'm trying to twist, right? You're exerting a torque on the lid to try to open a jar. That's one way to have a torque. This whole device was kind of like a wrench that would go around, like a rubber band would stick around the lid, and then there'd be like a handle sticking out here, and then you'd pull on the handle.
I think
So why does that?
use
What?
those same things for like oil filters.
Yeah, you do.
Yeah.
It's like a chip, like a bike chain.
Yeah. So, and the principle is true. If you ever try to like loosen a really tight bolt or something, and you're like, oh, this thing's not budging, you can grab a longer wrench, right? So I'm not sure if you're all familiar with that idea, but so if you're like, oh, they even sell like little extenders. So like, oh, I'm trying to say loosen this bolt and it won't budge. Well, that's because you're not exerting enough torque on it. So what you do is you get a longer wrench. Now you exert the force here, and it's way more torque.
So what
What?
is leverage? Like how does
What's-
leverage?
Because you're tightening the bolt. If you're going up, you're right. Right.
No, that would loosen it. It's anti-clockwise.
That's less.
Is it?
Yeah.
I don't know my direct. Wait.
Why do they say left and right? There's no.
It's how it's
It's clockwise tightens in the typical, bolt or screw. Clockwise tightens it and anti-clockwise loosens it. Right? Yes, they're opposite of clockwise. Or sure, if you want counterclockwise.
Real unsophisticated folks.
Anyway. So, same with your car wheel. Clockwise to go right. I guess it's not the same thing. You're not like tightening or loosening. Okay, sorry, where were we? All right, anyway. So torque. Torque is this symbol. Who knows what this symbol is called?
Torque.
No. That's what it represents. What's the symbol called? It's Greek. Theta? No, it's tau.
Ow.
No. Mr. Holt, so is that like leverage? Like what is leverage?
Same idea. Leverage just doesn't have like as far as I know, there's no like, it's a more general word just to describe this kind of principle. It's like, oh, you have better leverage if you're,
Right.
so suppose you exert 100 newtons of force, and let's say this wrench it's a really long wrench, it's 2 meters long.
Damn.
Well, your torque would be 200. What are the units of torque then if you're multiplying
Foot-pounds.
newtons by meters? Newton meters.
Wait, is okay, I guess.
No, okay, so if you're using American or imperial units, then yeah, your wrench, you might say, for example, here, I'll use a different one. Here. So say your wrench was 3 feet long and you exerted, this time we're going to tighten it. Say you exerted 40 pounds of force, right? How much torque is that?
120 pounds. I just know.
20 foot-pounds.
On like a torque wrench.
Depends on which one. A lot of bike wrenches will use a Newton meters because they're civilized. Yeah, so anyway, so torque is just, don't forget, like units are just units. So you can measure force in a lot of different ways. There's newtons and pounds are the two main ones. This scientific way, and then this is the imperial. And then like for distance, you can measure meters or feet, but you could have a torque of, I don't know, you could have Newton inches if you really wanted to. If you're measuring your force in newtons and your distance in inches, then Newton inches could be your units. Is this making sense?
Yeah.
Okay. So, there's your definition of what torque is. So it's just the force multiplied by the radial distance from whatever thing is being twisted, turned. Okie dokie. You feel okay? Feelings intact?
Yeah.
Okay, so, oh, and by the way, I gotta show you the toy again. Where did I put that? I got another one. Where did the?
Right behind you.
Oh, this one's way nicer. Pretty colors. This one's prettier colors. You guys remember this toy, hopefully?
Yes.
So I'll just quickly refresh your memory here because this connects to center of mass in a way. So like, simple example might be, if I take 3 of these and put them on, say, I don't know, the 4. So 3 times 4 is 12. I could then put maybe like 2 over here. 2 times 6 makes 12. And so there's, for the millions of Twitch fans, there you go. Well, prepare to be amazed. So if you recall this, those of you that figured it out probably figured out there's a multiplication thing going on here, right? You take the number of tiles and multiply it by the number, right, to get them to balance. So 3 times 4 is equal to 2 times 6. Yeah, feel fine? Okay. So you can think of that in terms of center of mass. If you remember, for center of mass, we took the mass multiplied by the distance. But you could also think about this in terms of torque, because what happens if you just have these? Well, this exerts a torque on the system, right, to turn it clockwise from your perspective, right? And then this exerts a torque in the other. So if I exert more torque over here, it's going to twist that way. But if I exert the same amount of torque, so notice it's the force is exerted downward. So force multiplied by radius gives you the torque. Is this like making sense? Okay. So anyway, I'm just trying to maybe help you connect those in your mind. There's when you have like a balancing system, you can think about it in terms of I've made the center of mass be in the middle, or you can think of it in terms of I've balanced the torques. The net torque is 0. Okay. So let's do number 1 together. So there's a revolving door. So the diagram shows an overhead view of a revolving door, and I don't know if you guys have ever done this. If you have like a younger sibling or something, and you got a door, and you're like, try as hard, like push as hard as you can. In this example, Bob would be the younger sibling who's been bamboozled. Say, Bob is pushing. Here's the force from Bob, and then you push on the outer end of the door, right? And then your sibling, of course, no matter how hard they try, they can't push the door. You guys know, anyone, Aiden, you've done this? Yes. cruel man you are.
Yes.
How old is your sibling?
13.
Perfect age difference.
That's still, yeah.
The classic trick is, I bet you're not strong enough to pick up this gallon of milk. And they go, look, I just did. And you go, well, you touched it last night to put it away.
Oh, yeah.
The ultimate ruse. Okay, anyway. So what I'm trying to say here is, the door does not move. Okay, so if the door does not move, then we can think about this in terms of torque. So we could say that if the door is not moving, then the torque exerted by Albert must be equal to the torque exerted by Bob. Do we all understand that basic idea?
Yes.
Because like if say Albert was exerting, spoiler alert, if Albert was exerting more torque on the system, then it would rotate that way, counterclockwise for you Americans. No.
Up.
Yeah, rotate up. Okay. If Bob was exerting more torque in the system, then it would rotate clockwise. So anyway, well, okay, how do we write this? Well, if Bob is in the middle, so let's call this distance, I don't know, this could be, for example, there's two ways maybe to think about this. I could say this is like the length of the door, and this could be half of the length of the door. That makes sense to me. Does it make sense to you?
Yeah.
Okay. So the torque that Albert exerts would be Albert's force multiplied by his radius, which is L. And Bob's torque would be the force exerted by Bob multiplied by his radius, which is half of L. And what's the relationship between FA and FB? Notice the actual length of the door is not relevant if it's all about the proportion, right? So this door can be a meter wide, it could be 3/4 of a meter wide, doesn't really matter. And we get this, we get interpretation. Albert only has to exert half the force that Bob exerts in order to balance the system, to keep it in equilibrium. Why? Because Albert's radius value with respect to the pivot point is twice as long. By the way, Julia, just to get back to your question about leverage, another way people use it is like, so really simple example would be like, say you're trying to lift something heavy. Show two different examples. So suppose you're using like a piece of wood, like a 2x4 or something to lift something. If you put the pivot point in the middle,
Fulcrum.
sure, the fulcrum,
Ooh.
and then say this is the rock you're trying to move, right? Well, the rock exerts a force, gravity force, and you're going to have to exert. You would have to, if you wanted to lift it up, you have to push down. Well, if this is the same radius, then you have to exert the same amount of force. So, but then what if you reposition your thing like this, where let's say that this distance, call it D, let's say your side of the stick is 5 times longer. Well, what that means is that whatever force the rock is exerting on the system, you only have to exert 1/5 as much force. So what that means is, say you're capable of exerting 100 pounds of force, well, you can lift a 500-pound rock if you have this ratio in your lever. So that makes sense?
There have been moments that have been so bad that I literally just dangle off. Yeah. Same idea, different example.
Okay, so let's look at number 2. Albert and Bob are going to sit on a seesaw. Seesaws.
Always fun until the person at the bottom gets off. Yeah, I would never was.
So as you know, on a seesaw, if Albert, here's Albert, if Albert is 2 meters away from the center, and Albert's 100 kilograms, does Bob want to be farther away or closer to the center? If Bob's only 80 kilograms.
Farther.
He wants to be farther away. So let's call this distance x. Here's Bob. What? Wrong side of time. So what's the equation? Well, I want to say that the torque that Albert exerts in the system must be equal to the torque that Bob exerts in the system. Okay? And so what torque let's look at Albert. How much force does he exert in the system? 980. I'm just going to write it as 100 times g, if that's okay. So think about, why would I want to write it as 100 times g? There's going to be a g on the other side. They're going to cancel eventually. But I do want to, just to be precise, I want to write force times distance is equal to his force. It's not as big. So he's exerting 80 g newtons of force. He's exerting 100 g newtons of force. 80 g. G's cancel out, or you don't have to cancel them. I mean, you could write this as 980 and this is whatever, 7 something. So, but in any case, what do you end up with here? Is it 2.5 or? Please help, someone help, Mr. Calculator. It's 5.4, so yeah, I think it's 2.5, yeah. Does that make good sense? Mm-hmm. And again, you can think about this proportionally with ratios. Bob is 4/5 as big as him, so his distance is 5/4 as big as the distance.
Oh.
It's all proportional.
Mr. Albert, can we do this where the board's actually has a big, well,